Okay, so the fourth experiment we're going to talk about is titration. And titration is a very common experiment for the IB to discuss in error analysis and for paper 3 in the first part, the part A, where you talk about laboratory procedure. And so for titration, the purpose is to determine the molarity of an unknown solution. Okay. So you're essentially you have a known solution and then an unknown solution, and you're reacting them together to figure out the molarity of the unknown. Now there's two types, and it doesn't matter which kind you do, it's still the same concept. You can have an acid-base titration, or you can have a redox titration. Okay, so it doesn't matter whether it's an acid or a base or an oxidizer or a reducer, you're still reacting molarities with molarities, and the idea is that the moles react with moles. That's the whole point. Like you're making it so that they both completely react, so that way you can come to a conclusion about what the unknown molarity is. That's the only way titration works, is if you reach a point where you know all of your known is reacted, so therefore you can figure out the molarity of your unknown. Okay. So you'll see this, and I'm not going to separate redox versus acid base because they have the same concept. It's not like empirical formula where you have significantly different characteristics of the experiments that we talked about last week. This is going to be the same for everything. So the equipment you need is the the following, the main pieces of equipment. Burette. Okay. So burette is to measure the volume of titrant, which is your known amount. So you're putting your known solution in the burette, and it's called your titrant. So you know how much you're adding, so you can accurately measure how much you're adding. Okay. We have our indicator. Okay, our indicator um, shows neutralization, usually through a color change, and that's true for acid base or redox. Yes, Christoph. Yes, correct. Yeah. Analyte is the one you're analyzing or your unknown. Okay. Now, whether it's acid base or redox, usually it's a color change that will signify when the reaction is complete. So in acid base, you usually add an indicator that changes, like phenolphthalein or stuff like that. Redox titrations actually change color themselves. So like there are a few kids in their IAs this year, they did like titration of vitamin C, and they'd use starch and iodine, and the iodine would change color from yellow to black when it was completely reacted. So like sometimes with the redox reactions, it's already inherently built into the reaction, so you don't need to add an indicator. But the idea, the purpose of an indicator, say, shows neutralization, shows when fully reacted. That's the purpose of an indicator. And last, you have a flask or beaker, which contains a known volume, excuse me, of your unknown, your analyte. Yes, correct. So that's what you're adding the titrant into and mixing. Yes, I guess you could theoretically. It's just that I feel that usually when we're doing these titrations, usually your unknown is going to have the color or a lack of color, and then when you add the titrant, it's going to change to the color that you want to achieve. For example, if you're doing a strong acid and strong base, if you start with a strong base, like even if it's your titrant in the flask, then if you put phenolphthalein in, it's going to start pink and you're going to go colorless. I think that's a lot harder to tell than flipping it. Yeah. So it just changes the order, but technically it could be the same. But if you're talking about general proper technique, you would put the unknown in the flask. Yeah. Okay. Now, tips. Okay. There are a few tips that you need to consider here. Okay. One, I've seen on previous exams, and I've uploaded all the previous exams in Schoology, so you can access them SL, HL, paper 1, 2, and 3. Remember, there's some years there's no paper 3, just a heads up. But they're all in there, so you can take as many practice tests as you want now and come ask me questions about that. But in some of these exams, the first trial is called a rough trial. Okay. The first trial is always the least accurate because you don't know when to slow down the first time because you have an unknown. So generally, you omit the trial from calculations. Like I've seen them have before, like they'll have a data table and say rough trial, first, second, and third titration. And you have to know that I do not include the rough trial in my averages or any calculations and stuff like that. That is just a test one so that you know where to slow down so you can be more accurate in the real ones. So there are such things as rough trials. A personal thing, I don't like to start at 0. Okay? Because when you start at 0, you have less significant figures there. It's harder to reference and relate to the correct volume reading the measurements of the meniscus. Okay? 3. Okay? Rinse burette with distilled water, but last rinse is of titrant. Okay? So, yes, you rinse your beer out with distilled water a couple times, you run it through, but the last time you run it through, you should add a little bit of titrant and rinse it through with the titrant that you're about to use. Okay? What's the purpose of that, you think? What's in the burette if you're rinsing it with distilled water? Mm, just water, distilled water. What happens when you add a titrant that has water left in the burette? It's going to be watered down. It's going to be diluted. So that's going to throw off all your calculations because you think it's a certain molarity, but with that excess water in the burette, it's actually a lower molarity. So you end up having to use more, which we'll talk about as a source of error later on. Exactly. So the last rinse should be of the titrant. This is kind of one of those things where, like on the paper 3, they might say a student rinsed their burette with distilled water and then performed a titration. They found their molarity to be too high, suggest one reason for why that might be the case. So you would say, well, water left in the burette would dilute the titrant, so the molarity of the titrant would actually be lower than expected, which means it would require more volume, which would make you think the molarity was higher. Paper 3 and sometimes the last part of paper 1, multiple choice. Like 38, 39, or 40 are sometimes lab questions. So, but the short answer ones, so I would say paper 2 is more of a calculate, like the first question on every paper 2 is usually a lab-based calculation question. Paper 3, it's more a student performed this experiment, talk about like what they did right and what they did wrong, less so actually calculating things in there. Okay. So, 4, record volume after color change is permanent. If you remember some of these titrations, sometimes the phenolphthalein would turn pink and then it'd fade away, turn pink, then fade away. That's part of the reaction occurring. Yes, Christoph? Yes, yes, to accelerate the reaction so that we would have less likelihood that it would like appear to stay pink for longer and we think we'd be done. So yeah, anytime you are waiting on something, stirring and mixing will speed up the reaction so that there's less room for error. Okay. 5, only use a few drops of indicator. Okay. Only use a few drops of indicator. Do not pour a bunch of indicator in there because the indicator is usually a weak acid. And if you put too much indicator in there, you'll end up titrating the weak acid indicator along with your acid that you use. So only use 2 or 3 drops. That's plenty for you to observe a color change. Okay. So only use a couple of drops of indicator. That'll be plenty to show the entire solution change in color because you don't want it to interfere. Okay. Sorry, I hope we're running around room in this box. Well, y'all probably can put this somewhere else too, but like, let me zoom in a little bit here. Making a solution. Sometimes for the titration problems, they'll ask a student to outline how to make a solution. And so the key things you want to say, okay? What type of glassware do you make solutions in? Nope. Close. What type of flask? Nope. It's a
What's
specific,
it called?
Brooke,
Like the round, I can't remember what's it called.
it's called a volumetric flask. Okay? It's the one that's skinny at the top and then round at the bottom. Okay? A volumetric flask has one line in it that represents that specific volume, and that's what you should make solutions in. That's the proper way to make a solution is use volumetric flask for everything. What? Oh yes, yeah. There's a scene in Breaking Bad where he talks about a volumetric flask versus a round bottom flask, right? For heating, you never heat a volumetric flask. Sure. Okay. Now, generally, what you do is a couple of things. Okay, if you're making a solution of acid, you half fill with water, then add the solute. Whether that's the acid or a salt or a compound, you're going to add that amount of solute into the water. You always add acid into water. You never add water into acid. So always add acid to water and then dissolve. So then mix and mix until it's completely dissolved and then fill to the line. Okay, so you use a volumetric flask, you use distilled water, you fill it halfway with water, you add what you're going to dissolve in there, you mix it, make sure all dissolves, then you add water to get to the line, and then you're done. It's really hard to mix when it's completely full. And sometimes the volume will change if you, even when you if you fill the water up to that line and you add something to it, your volume's going to change. And so you don't fill up to the line until you're completely dissolved everything in there before you do that. You all right? Okay. Oh, it's mine. Yeah. Okay. So those are the procedure and laboratory techniques that you need to be familiar with titration. Okay. Now, data collection, you need to know what values that you need to know to for the analysis. One, molarity of the titrant. So of your known solution, you need to know the molarity. Okay. You need the volume of titrant, which is your volume of the final minus the volume of initial in the burette. Okay. Remember, burettes count downward, so your number at the end will always be larger than the number that you start with. So you will get a positive number. You'll also need to know the volume of the analyte. And you'll need to know a general identity of the analyte. Is it a monoprotic acid or a diprotic acid? Okay. What does monoprotic mean? Huh? No. Break down with the term monoprotic. Mono means what? One. Protic means just what does it sound like? Proton. So a monoprotic acid can donate one proton. A diprotic acid can donate two protons. Because that matters because the last thing you need to know is a balanced equation. So a monoprotic acid will react differently than a diprotic because a diprotic will absorb twice as much analyte than a monoprotic will because it has twice as much H's to neutralize. Okay. Okay. And so the general idea is this. These two values get the moles of the titrant. And then if you use this, you can convert to moles of your analyte. And then you can divide by the volume of the analyte to get the molarity. And I'm gonna walk you through that in the analysis section. Don't worry. I'm just kind of showing you why each piece of data is important for this experiment. No, what you don't know. You're analyzing it, which means you don't know it. Titrant is what you know. Analyte is what you don't know because you're analyzing. Okay. So your analysis first, you want to get your average volume of titrant used. So you can do all your trials. You average the volume of titrant used, so that way you can just do one calculation. Okay. And to find the moles of titrant, you need to multiply your molarity times your volume. But remember, molarity is what unit? Mm, what? Not liters, decimeter cubed. And volume needs to be therefore in decimeters cubed. So make sure that you make sure your units are matching. That's a big mistake that students can make. Okay. Now, once you get the moles, then you can calculate the moles of analyte by using the mole to mole ratio. So if we know the moles of titrant and we know the balanced equation, we can figure out how many moles of analyte must have reacted with it. And then, the last but not least, we can calculate the molarity by doing the moles of analyte divided by the volume of analyte in decimeters cubed. Make sure your units are matching. It's a liter is 1 decimeter cubed, but generally in these titrations you're measuring in centimeters cubed, and 1,000 centimeters cubed is equal to 1 decimeter cubed. Now, if you like the proportion method, if you like to do that, there is a simple way to kind of rewrite this to make it all into one step. And so the molarity of the acid times the volume of the acid over the molarity of the base times the volume of the base is equal to the moles of acid over the moles of base, the mole-to-mole ratio. So if you do that, if you multiply the volumes and the molarities and you cross multiply with the coefficients of the reaction, you can actually solve for your one unknown. You should only have one unknown in these problems. Yeah, generally, but it could be anything, right? They could ask you what volume would you need, and you could still do it if you knew the molarity. Yes, correct. So you can use this in a lot of different ways. Wait, what? Yes, correct. So, sorry, I didn't follow your question. Yes, so you might be solving for VA, which means you'd have to. So you might be solving for MA, which means you'd have to know VA, MB, VB, and then the mole ratio. Or if you're solving for VA, you'd have to know MA, MB, VB, and then the mole ratio. Yes, correct, correct. Hmm. Yeah. Correct. Yes. Yeah. Now, Christoph, I could say this though. Technically, they could give you four, but you couldn't figure out the molarity volume, but you could figure out how many moles reacted. Like, let's say you're titrating a solid, then you don't have a molarity and volume. You just have a mass, and you have the number of moles that you react. So technically, you need to remind yourself that this is the same thing as moles, and this is the same thing as moles. So sometimes you might be just solving for moles instead of solving for individual molarities or volumes. Yes, correct. So you can use that for a variety of different things. Okay. Now higher level, don't forget when you have a titration curve, you have a couple of major points here. The equivalence point, which tells you the volume that you need to react if they give you titration. But if it's weak, this point is also very important. Halfway to the equivalence point, because at that point, pH equals pKa. Possibly, yes. Like instead of giving you a data table, Christoph, they could just give you a titration curve. And then SL would have to use the equivalence point to figure out the volume that was used. And then there might be an additional question for HL that says, what's the pKa of the unknown acid? So you have to find halfway to the equivalence point the volume and then go straight up and go, okay, the pH is 4.5, so the pKa is also 4.5. Yes, this is pH. Correct. Correct. Yes. Halfway to the equivalence point. Exactly. Okay. Questions? Okay. Yes. Correct. For standard level and higher level, this is where you use negative logs and things like that. Because you have to convert pH to H plus or pKa to Ka and vice versa and stuff like that. So yes, this is the one topic where you're using logs quite a bit. They only give you pH equals negative log of H plus, but that's implied that for any you can plug anything you want in there. Correct. pH, pKa, pOH, pKb, pKw, all those are the same equation. Correct. Okay. Oh, I didn't have random error in there. Okay. Random error. The big random error that you might have is reading the meniscus. Because if you're not eye level, your values will be off. Because you're going to look at it from here and you're going to think it reads like that. Or if you look downward, it's going to look like this value. But let me ask you this. In this experiment, if you read the meniscus the same way every time, does it matter? No. Why? Still initial minus final. So if you're going to be off by the same amount in both values, the difference will still be the same. So this actually has no effect in titration if you're doing it the same way, because you'll get the same change in volume, delta volume. So whenever you're doing the difference and stuff, having error like that doesn't matter because you're just looking at the change. Okay. Questions? And remember, random error can always be solved by more trials, because the idea is that random error means it can be up or down. So if you do an infinite number of trials, it will eventually average out toward the accurate, because half of them will be too high, half of them will be too low, and it'll average out toward the norm. So random error is always more trials. Systematic, it doesn't help you to do more trials, because systematic, it's always too low or always too high. So whether you do a billion trials, it's always going to be too low. It will never go toward the actual correct value. So systematic error is, I have something wrong in my procedure, it's not accurate, so I have to figure out what's wrong. Okay, so we said a couple of these in our discussion ramping up to this. One, water in the burette. And I'm going to talk to you about more specifically how this affects data, because that's what you're really tasked to do on paper 3. Okay, water in burette dilutes titrant. So therefore you have to use more titrant. And so therefore the molarity of the analyte goes up. Because you may think you're using 0.1 molar, but maybe you're only using 0.09 molar, but you're using the volume that you think is 0.1, so that'll make you think you have more moles of acid, so therefore then your molarity will go up. So diluting your titrant makes you appear that you're using more titrant than you need to be. Okay. 2, too much indicator. Okay, you end up titrating the indicator along with your unknown. So you end up neutralizing the indicator as well, a significant amount. So therefore, it'll throw off all your data. So only 2 drops. 3. This is one that comes up a lot in the questions. Adding titrant too quickly. Okay. What do you think happens if a student rushes through the experiment and ends up adding too quickly the volume of titrant? What happens? You overshoot, right? You go past the equivalence point. So therefore, you're adding too much volume, which then again increases your molarity because you think that you're using more than you actually need. So that's why, like, when you get to the dark pink, we usually tell you to start over because you went too far. It has to be a pale pink. Now for higher level, okay, you want to make sure one of the errors you can have is choice of indicator, because you want one that matches or gets close to the equivalence point. You don't want one changing color at a different pH than the equivalence point. So you have to know, okay, what kind of acid, what kind of base am I reacting? Therefore, I know what kind of indicator that I want. Okay. Yes, you look at the indicator chart in the data book, like Christoph. Now, if you react a strong acid with a strong base, what kind of salt are you getting? Strong acid, strong base, what kind of salt are you getting? The choices are acidic, basic, or neutral. So strong acid plus strong base gets you what kind? Huh? Neutral. So this is a neutral salt. So you'd want something around a pH of 7. A strong acid plus a weak base, acidic. Exactly. Oops. So you want something less than 7, like maybe 4 or 5 pH change. And conversely, weak acid plus strong base is basic. So you want an indicator that changes above 7. And like Christoph said, there's a chart in your data booklet, which we'll flip to in a second once y'all write this down, that you can refer to figure out, because they'll ask you, like in paper 3, suggest an appropriate indicator for the titration. So you have to be like, well, it's a strong base plus a strong acid, so I want something around neutral. Or it's a strong acid and weak base, so I need something less than neutral, lower than acidic. Yeah. Well, no. There's no obvious way you can tell, so they're not going to make it that. Because depending on weak acid, weak base, then which one is a stronger weak acid or stronger weak base is the one that determines it. But they're not going to do that to you. So for higher level, you can scroll down to this section right here, table 22, acid-base indicators. And again, looking at these indicators, the way you read this is this. When it says pH range, that's the range in which it changes color. So you want the pH range to match what you expect the equivalence point to be. And then the pH range will fit in between these. So if don't let the word acidic and alkali fool you, because what they mean is acidic or alkali relative to this. So for example, in methyl orange, 3.1 to 4.4 is right here. So acidic is less than 3.1, not less than 7. And alkali is more than 4.4. And if you're somewhere in between 3.1 and 4.4, what color do you expect to see? Orange, a mixture of the two colors. So that's what you want to think about here for higher level is these ranges fit right in here. And if it's less than that range, it's this color. If it's more than that range, it's this color. If it's right in the middle, that's what color. So maybe they'll say suggest a indicator and state the color change or what color it should be at the equivalence point. So you would just you'd have to kind of do review your colors. Blue and yellow make green. Red and yellow make orange, things like that. Colorless and pink make pinkless. No, I'm kidding. Okay, so it'd be a pale pink. Now we use phenolphthalein. Okay, let me ask you this. This is kind of a thought question. Phenolphthalein changes at 8.3, not at 7. So what might be one reason that we use phenolphthalein instead of bromothymol blue or phenol red, even though those change more closely to 7? Christoph. Yes, let's assume. Okay, so let me rephrase that. Let's assume we're going with the neutral salt. Let's assume the salt is 7. Can you think of a reason why we would look at phenolphthalein versus bromothymol blue or phenol red, more practically speaking, not chemically speaking, more practically speaking? Why do you think we would have you do phenolphthalein instead of these other two? Think about what you're trying to identify. Exactly. It's easier to see the color change, yeah. Because like yellow, red, what orange are we talking about? Yeah, yellow, blue, what green are we talking about? But pale pink, really, really obvious. So the practical reason why we mostly do that in high school is it's easy to see pale pink. It's easy to stop there when I can't tell you, okay, this orange is what you're trying to go for, or this blue or green is what you're trying to go for. But pale pink is very easy to describe. Yes, Christoph. Oh, it'll be dark pink. No, even over 8.3, it becomes dark pink. Yeah. So yeah. Yeah. So that's why they say very, very light pink. That's as close to 7 as you can get possibly you can get. Yes. Yes. Yeah, bro, phenol blue. No, it'll be a mix. So if it's in between, it'll be a mix. So you would say green. Yes, because that's what the color it is when it's completely on the other side, and the color on the other side. Correct. Right. Like let's say you use bromopheno blue for a weak acid strong base. That changed at 9, but you're gonna change at 4 here. So even when it turns blue, that helps doesn't help you at all. So that's why choosing an indicator is super important. Does that make sense? Oh, yeah, yeah. The name doesn't necessarily tell you anything. You'll have this whenever you need it. Okay. Questions. Let's take a 5-minute break, and then we'll come back and we'll talk about some analytical chemistry.
I do have a question. What, which
Yep.
topic do I put this under?
This is topic 11/21.
Okay.
If you're trying to find a place for it. Okay. So again, this is not an in-depth topic 11/21 review. This is kind of a Cliff Notes version of it so that you understand like general idea. What am I trying to get from NMR? What am I trying to get from mass spec? What am I trying to get from IR spectroscopy? Okay. You know what? Let me do it as a table. Yeah, let's do it as a table. Okay. Haven't done this before, so bear with me. But um, let's see. How do I want to do this? We'll do mass spectroscopy, IR spectroscopy, and NMR spectroscopy. Again, I haven't done it as a table before, but this could be a different way to look at it. Yes, I'm going to keep a small column on the left and try to fit as much as I can in there. Okay. Again, this is experimental. I'm not sure how this is going to work, but I think that'll make it work. Okay. So let's go with um, what it measures. Okay. So mass spectroscopy measures the mass of fragments that are all cations. That's important. Massive fragments, and they're all cations. IR spectroscopy measures the IR absorption of bonds. NMR spectroscopy talks about radio waves um, dependent on hydrogen spins. Okay, so you're measuring the radio waves that are essentially um, emitted by the hydrogens in the organic molecule that are spinning. I'm kind of using buzzwords in here because these are the buzzwords that should kind of trigger you to go, okay, IR spectroscopy is IR bond absorption. Radio waves should always be associated with NMR. Mass is always mass spectroscopy. They are significantly different in that case. Oh, dependent on hydrogen spins. Let me clean that up a little bit. Fair. Definition. So we're gonna start commenting on this video, Jada, about you. No, it's good. Y'all saw that comment, right? There's one video we recorded earlier this year, and someone that we don't know said, like, I've almost memorized Jada and Amon's voices because they asked so many questions. It's a term of endearment. Don't worry, Jada. Okay. All right. So it measures massive fragments, IR, and then radio waves. Okay. Let's see. Oh. Okay. Um, what information does it give you? Okay. This will tell you the molecular mass of the compound and possible functional groups. Now, it doesn't tell you a lot of detail about those functional groups other than their masses. So yeah, if there's a function group if there's only one function group that has that mass, then it's obvious which function group it is. But there are some function groups that share the same mass, so it doesn't tell you anything more than that unless you have other information. Okay. IR spectroscopy is the types of bonds present. So IR spectroscopy with the diagram they have will tell you, okay, there's a C double bond O, or there's a CO single bond, or there's a OH bond in there. So that's the idea of the information you're trying to get from that, is the types of bonds present. Now, that can also lead to functional groups as well, because if you know there's a C double bond O, then you know there's at least either a ketone, aldehyde, or carboxylic acid, or ester present. So there are some kind of characteristics about that that can tell you that as well. But the main idea is bonds present. NMR spectroscopy tells you which isomer is present. So the point is, NMR spectroscopy is to tell you, okay, I know the formula, but based on NMR, I can tell you which structure is the correct structure for this, and where are which bonds. So here you're going to be looking at environments, splitting patterns, integrated trace, and shifts. Yes, we will talk about that a little bit more. Okay, I'm going to keep going down here.
You should scroll up a bit.
Oh, yeah, sure. Here.
Yeah.
The next thing we're going to do is sketch a very, very rough sketch of what the graph might look like. So that way you can kind of differentiate between what you're looking at here. So an a mass spec will kind of look like this. So you'll have these peaks that show, and remember the rightmost peak is the molecular ion peak, which tells you the molar mass of the known compound. So the furthest most right one is the molecular ion peak, which is the mass. I guess the furthest most significant one. There might be a tiny one after that, but that might just be an isotope. So the most significant last one. Okay. Parent ion peak. Parent ion peak is another term, correct? For IR spectroscopy, you're going to see something like this. Oh, you know what? Let me label this as well, because I guess you should know the labels for this. So this is mass or MZ, and this is abundance. This one is wave number, and this is absorbance. Oh, sorry, transmittance. Because when it dips down, it's absorbing, so the transmittance is going down. Yes, Christoph. Trace. Yeah. We'll dissect those terms because I think NMR is the most complicated one to talk about. So we'll dissect those terms on a separate piece of the notes here. But right now, I just want y'all to compare and be able to differentiate. Yes, Oliver. Oh, that gives you the molecular mass. So the rightmost peak on mass spec, so oh, the peak happens at 44. That must mean the molecular mass of the whole molecule is 44. Now, remember, there is a section that's 1500 or less that is very um, kind of muddled. Do y'all remember what that's called?
Identity? So?
Uh, no. There's the region, fingerprint region. Yeah. So it's called the fingerprint region because no individual peak is useful, but the overall pattern is useful, like your fingerprint, right? You can't identify someone based on one whirl or one arch or one loop, but when you have the whole combination of whirls, arches, and loops, then you can have a picture of it. So the fingerprint region from 1500 or less is called the fingerprint region. Too many bonds absorb. Right. So you can't use individual bonds there. Okay. Actually, NMR will look kind of like this. Okay. Oh, you know what? Let me put one here too. No, it has three environments. You're close. I drew that last one on purpose. Okay. The one at zero is not an environment. Do y'all remember what that is? It's a reference. Close. Yeah. T. You're really close. You got two of the letters. TSM. Oh, no. It's TMS. Sorry. It's TMS. Tetramethylsilane. So this is TMS. So that peak is not a peak that we treat environment. So Jada, how many environments are in this diagram? Three. Exactly. And the splitting patterns, the one on the left and the one on the right have what kind of splitting pattern? Singlet. And the middle one has, um, that's how many peaks are in there. So it's a triplet. Okay. Good teamwork. So a singlet versus a triplet. Okay. So we do need to know splitting patterns. So there's three environments. Let me write that down. Three environments. This is a singlet, and a triplet. So the number of peaks inside each environment has a name as well. No neighboring hydrogens, exactly. And the triplet has two neighboring hydrogens. Good. How's the maple? It's very mapley, huh? Oh, tetramethylsilane. Maybe if you want me to move on. Tetramethylsilane. So just a reminder, again, this is one of those things that's in your data booklet. When you go to this section of the data booklet, they'll literally say they're relative to tetramethylsilane for HL. So they tell you all the shifts are relative to. So you don't necessarily need to memorize what TMS is. It's in the data booklet. Now, and down here is the shift. The shift tells you the functional group. And we'll dissect that a little bit more later on, more specifically. But yeah, we'll look at one and we'll analyze it for NMR. But I still have some more stuff I want to add on this chart. Oh, oh man. Okay. Too cool. Okay. That's a different color. I just realized that. Okay. Um, Common mistakes that students make. Okay. One, the fragment responsible, if they ask you that, it needs to be a cation at all times. So if they ask you, state the fragment responsible for this peak, it needs to be a positive. I don't care what it is. I don't care if it's CH3, it needs to have a positive sign on it. Okay. If they say fragment lost, then you don't have to write the charge. So if it's a CH3 that's lost because the mass has decreased by 15, then you just write CH3. But if they say fragment responsible, you have to write a positive or you'll lose a mark. And that's a silly mark to lose when you get everything else right, right? Again, we're trying to minimize silly mistakes. We're trying to minimize losing points for things that you know. So make sure you write those positive charges. Now, IR, um, knowing what the fingerprint region is and knowing to try to avoid those peaks. You don't label those peaks. And also, um, sometimes peaks overlap. So sometimes there are peaks that overlap. Some of the broader peaks will kind of cover up other peaks. And so make sure that you're kind of wary about that. Okay. NMR, there's a few things that you have to be careful about. Um, Reading data table for shifts. Because you have to look really closely, but in data booklet, the hydrogen in question is bolded. And so some of them look very similar, but the H that's bolded is different in those examples. So you have to really close attention to that. And then the integrated trace measurement. So you are given a ruler in case you run into this scenario where they give you like the integrated trace, and then you have to measure the lengths of each of these. And then the ratio of lengths equals the ratio of hydrogens. So the ratio of the length is the ratio of hydrogen. So if you get 2 centimeters to 6 centimeters to 4 centimeters, that means there are, for every one hydrogen in the first one, there's 3 hydrogens in the second environment, and there's 2 hydrogens in the third environment. So make sure you're measuring those correctly. Make sure that numbers make sense. Sometimes rounding is kind of weird, but like, let's say this. Let's say your compound has 9 hydrogens, but your ratio is like 1 to 3 to 4. That doesn't make sense. Because 1 to 3 to 4 is how many hydrogens? 8. But you have 9 in your formula, so 9 and 8 don't mesh. So double check your measurements and see if there's something that you did wrong in your measurement. Maybe you read it wrong because the numbers should make sense. So like if you have 8 in your ratio, it should either be 8 or 16 or 24 in your formula. It can't be 9 or 10. If it's 9 or 10, you did something wrong. That should be a red flag. If your ratio doesn't make a factor of the number of hydrogens you have, that's a red flag. Mm-hmm. Oh, then they probably gave you the formula. Yeah, if they give you the formula, then you can just count the hydrogens in the diagram itself by identifying the environments and then just counting how many are in each environment and then find the ratio. Questions? Okay, let's see. Is there anything else I want to say on these tables before we move on? No, I think that's it. I think that's a good chart, actually. I think that's very useful. Compare them. I just came up with that just now. Oh, I don't know if I told some of y'all, but final Tron talk this Friday. So, yeah. So, yeah. Huh? So, um, let's see. Now, oh, sorry, Brooke, you still need this?
I'm good.
Okay. Let me find one here that I can use for this to kind of talk about it. Let's say, oh, we'll do this one. Okay. I think we would do this one in class, but I think it's still good. And you could probably sketch it yourself if you wanted to. Um, it has 4 peaks, 2 short, and then 2 taller in the middle, and then 1 peak, and then 2 short with 1 tall in the middle here. So ethanol looks like this: CH3, CH2, OH. Okay. Now, there's a lot to unpack in the structure that is reflected in the NMR spectroscopy. Okay. One, and you can do it either way. One, you can look at the structure and tell me what the information is, or you can look at the NMR and tell me. You'll be given one or the other. You won't be given both necessarily. So you have to be able to figure out both ways. So according to the chart, the graph, how many environments are there? 3. Okay. According to the structure, how many environments are there? How many environments are in the structure here? 3. Okay. What are they? Okay. This one, and this one. Because remember, you're looking at where the hydrogens are in the structure itself. Okay. If they're next to different hydrogens, then you're going to have a different environment here. But remember, symmetrical ones, you can have the same environment on both sides, which we'll talk about in a little bit. Yes. So if you have a symmetrical structure, Oliver, and the CH3s are both on its ends, they're the same environment. Okay. So according to both, we have 3. Spoiler, if you get different answers for the structure and the graph in this example, then you did something wrong. There's something wrong with your logic, but that's okay. Let's figure that out when we're reviewing instead of figuring out the hard way in on the test. Okay. So there are 3 environments. Okay. 2. Splitting pattern. Okay. What kind of splitting patterns do we have in the graph here? 4 is quartet, quartet, singlet, and triplet. Okay. So you have a quartet, a singlet, and a triplet. Okay. Let's look at one of these environments here. Let's look at this pink one over here. What kind of splitting pattern should this one have based on what it's around? How many neighboring hydrogens does it have? Nope. 2. This is the environment. There's 2 neighboring hydrogens. So what should it split into? Triplet, right? It's the number of neighboring hydrogens plus 1. So it's 3. So that should be a triplet. What about this red one in here? How many neighboring hydrogens does it have? Only neighboring carbons. 3. So therefore, what kind of splitting pattern should it have? Quartet. This one on the O has no neighboring hydrogens. So it should have a singlet. So there we go. We verified that we are correct here. Of neighboring hydrogens plus 1. Because the environment itself has one splitting, like its own peak automatically. Okay. The third thing is the integrated trace. Okay. Now this one, they wrote it for you. The number in red is the integrated trace. So what is the ratio of hydrogens in these environments based on our integrated trace here? 2 to 1 to 3. Or 1 to 2 to 3, whatever order you want to write. They'd have to give you a line. Yeah, and you'd measure it. Yeah, they'd have to give you the line. Correct. Now, what are the ratios of hydrogens in our structure that we've drawn over here? Yeah, 2 to 1 to 3, or 3 to 2 to 1, whatever way you want to write it. So that matches up, right? So that's the third thing you want to think about. Okay. The last thing is the shifts. Okay. So this H must be this OH here. This one must be the CH2, and this one must be the CH3, based on number of hydrogens that are in each environment. Okay. So we look at our chart here. Okay. We look at OH. OH goes from 1 to 6. Is that singlet in between 1 and 6? It was at 4, so that's correct. Okay. CH3 groups tend to be around 0.9 to 1. Okay. Is that CH3 group close to 1? Yeah, pretty close, like 1.2. That's fine. Okay. Now, this CH2 group is a CH2 on the other end of an OH, which is this one right here, right here, which is about 3.3 to 3.7. Actually, wait, is that? Yeah. Okay. Sorry. I thought the hydroxyl group was like further down. Like, wait, is that right? So 3.3 to 3.7. So that's right. So they all match up with the right structures in here. Um, like, okay, let's see. So what would they ask you about shifts? Okay. Um, they might give you a structure and give you an NMR and say, like, which peak is which hydrogen environment is responsible for the shift at 2.6. So you have to look at the structure and like, oh, the table says 2.6 should be OH or something like that. Does that make sense? Yes, correct. Yes, correct. So you're kind of interpreting there. Sorry, one second. One second, sorry. So I think NMR is the hardest. Now, having said that, most of this NMR is higher level stuff, like shifts, integrated traces is more higher level stuff. But I see the thing is, I think the IB is very vague about this for SL, so I still teach the SL because they might try to find something to ask about it that's not directly stated in your curriculum, but they might argue that it's something you should know. Okay. Questions? Okay. One last type of um, one last type of analysis that we have to know that's not in anything else. X-ray crystallography. Again, you don't need to know how to analyze it itself. You just need to know what it is. Okay, it uses X-rays to determine bond angles and bond lengths of crystalline lattice structures. So if they say something about using X-rays, that's X-ray crystallography. If they say something about bond lengths or bond angles, that's X-ray crystallography. But you are not required to interpret X-ray crystallographies in core curriculum. In option A, analytical, you do talk about like actually calculating the bond angles and bond lengths, stuff like that, but not for core stuff. So NMR, IR, mass spec, X-ray crystallography. These are the types of questions that will show up on paper 2 and the very end of paper 1. Like for a higher level, multiple choice, maybe 37, 38, 39. 40 is usually like a measurement one. And then SL would be like 28 or 29 would be that. Like, for example, oh, sorry, I'll give you a chance to write that down. No, not really. No, I don't believe so. No, I don't think so. Yeah. Those are more practical experiments where you're conducting the whole experiment yourself. So, for example, I think y'all recognize on paper 1, the question they asked, oh, okay. Like, they were asking about here, like this one. What information about 2-hydroxybutanoic acid can be inferred through mass spectroscopy, infrared spectroscopy, and proton nuclear magnetic resonance spectroscopy? So, mass spectroscopy should be the molar mass of the structure. IR talks about the types of bonds and the function groups that are present. And then HNMR tells you what type of isotope you have. So it tells you where the location in the structure where all those bonds are. So not isotope, isomers, excuse me. Isomers, bonds, mass of structures and things like that. And then, oh, I didn't even see 39. 39 asks you what information can be deduced through X-ray crystallography. That is B, bond angles. C would be mass spectroscopy. The bonds will break during fragmentation because fragmentation should be a buzzword for mass spectroscopy. Boiling and melting points, no. You don't need to know about the ionization energy, no either. Oh, because it'll change the number of environments, Jada. Yeah, yeah. So you think isomers because the number of environments changes where you move the OH. Do you remember like in class we practiced we drew three isomers out and said, oh, this one has four environments, this one has three, and this one has three? That's what they're talking about here. They're just phrasing it differently. Okay. Questions? Okay. All right. I think that's a good stopping point. I think y'all did a great job today. And we're finishing a little early, short session today, but I think we covered what we wanted to do: titration, and then also really brief NMR, mass spec, and IR review, just to kind of remind you of stuff. So I'll upload this on YouTube, and then y'all can